potential due to dipole is a point of our discussion. We have done the derivation in the previous class for the electric field and the potential along the horizontal line and the vertical line. Along this horizontal line, it is also called as axial line of the dipole. And also along the line, it is called as equatorial line of the dipole. The derivations we have made already in the previous class. Those derivations are applicable for any point only on the line, that is only along this line and these lines. But we need derivation for those field and the potential for any point in the space, for any point in the space around the dipole. This is a dipole. So dipole means the two charges are separated minus q and plus q by a line. It is called a dipole. This dipole has produced electric field in the space around it. So we need to calculate, we need to derive the mathematical expression for the field and the potential at any point in the space around it. That is what we want here. That is what we are looking at that. Now we shall go for the derivation. So let us concentrate for the derivation. Let us concentrate on this vector. What is the vector? This vector is called as dipole moment of the dipole. Dipole moment. This P vector is called as dipole moment of the vector. So the direction is along this line from minus to plus. This is the direction of this vector, dipole moment. Now we shall resolve for the derivation purpose. We shall resolve this vector into two different components. Because in vector algebra or in vector mathematics, we can resolve a vector into a vector of two different components like this. We have resolved this P vector into this vector and this vector. They are perpendicular to each other. So this is a resolution. So we have resolved this vector into two components. What is meant by resolution of a vector? Let me recall the mathematics of resolution of a vector in brief. Let us not go in detail about this mathematics. This is not required in this derivation. Just to understand about what is the resolution of vector, how the vector is resolved into two components. Just recalling this. The mathematics of vector. I am recalling this mathematics of vector. That is a position I am taking. A point in the space. This point is located using R. So this means a distance of this point from this point. This point is a reference point, origin. So R, the line represents the distance of separation of these 2 points, and this line is making theta with this x axis. To locate this point using what is the 2-dimensional coordinates, that is x and y in plane. That is x coordinate and y coordinates. This line is making another theta with this, and this is the distance between this point and this point. This is a vector. So this R is a vector representing the position of this point in the space with respect to the origin. So this angle represents the direction of the vector, length represents the magnitude of the vector, magnitude of the vector. These two are called as polar coordinates. These two are called as polar coordinates, and these two are called as Cartesian coordinates. These are Cartesian coordinates. This location can be specified using Cartesian coordinates as x and y. What is x? This length is called as x. From this point by a perpendicular line like this. This length is called as x value. This length is called as y value. So these are the values of x and y locating the position of the point in the space. These are called as Cartesian coordinates. Now we can convert. We can write these Cartesian coordinates into polar coordinates. How it is possible? It requires simple geometry. I already drawn a line, straight line. This straight line. With this straight line, we have a geometrical shape like this. This is called a right angle triangle. This right angle triangle making angle theta with this x axis. For this right angle triangle, write what is sin theta and cos theta. What is sin theta of this? What is cos theta of this? Sin theta of this is opposite by hypotenuse, that is y by r. Cos theta of this is adjacent by hypotenuse, that is x by r. That is so you can write what is x in terms of the polar coordinates. R and theta is r cos theta. It becomes r sin theta. That is x and y in terms of polar coordinates. Now this length, this length is called as r cos theta. This length is called as r sin theta. So this is a vector. If this is a vector, that is a position vector, this vector can be resolved into two components like this. These two components are perpendicular to each other. So this is resolved into x as r cos theta. It is called as horizontal component along the axis. And y as r sin theta along the, that is vertical, along the y is a vertical component. This is vertical component. So this is how the position vector, a single vector, it can be resolved into two different components. If the vector have the direction in this fashion, this is a vector direction, this is a vector component, this is a vector component. So we can represent this or resolving this into this component and this component. This component is called as horizontal component. This component is called as vertical component. So r is resolved into r cos theta and r sin theta in the same fashion. So this is the mathematics of what is that a vector, which can be extended to this as well. That is why I have done this. So any vector, any position vector in the space can be resolved into two different components of vertical two different component of two vertical, what is that, 90 degree at vertical angle with each other. That is the two components. So the same thing I resolved here. I have taken this is a vector, I have taken this line is what is that resolved into this line and this line. So this line is p cos theta, similar to this r cos theta. P into p cos theta, p into p sin theta. So p cos theta means it is horizontal component. This must be, that is a vertical component. So likewise, their vector is resolved into these two components which are in vertical direction. That is what the idea. We applied this over this. Now, what is the idea here? So after this resolution, let us keep a point of this line. There is a vector point where we need to find out what is that derive the expression for this field and the potential at this point. If the point is placed here, now if the point is here along this axis, that is axis, if the point is here, these two lines have coincided. This line is coincided with this line and this line with this. That is the original position. If the point is moving from this point to this point, so now what is that? These components will what is that move or rotate in the plane like this, with this angle. So this position or displacement, that is changing the position in the space, can see or measure in terms of theta. What is that? Angle of rotation of these two components. That is same angle of rotation. So obtain the form what is rotation of these vector components in the plane. Different position, if the position change like this, angle increases. It will appear as a rotation of these two components in the plane. That is the representation of these two components. That is the position I am talking about this. So with this point, so you have to keep this point as a reference point where you are supposed to find out the mathematical expression for the potential and the field. Now let us recall derivations you have made in the last class. That is the field derivation for the mathematical, that is derivation for the electric field along the horizontal axis or axial line. This is the derivation. And also derivation along the equatorial line. That is a derivation for the field along the equatorial line, derivation for the field along the axial line. That we have done the derivation in the last class. Look at that electric field is a function of what is that? P. This is a vector. That is a dipole moment of the dipole. It is also dipole moment of the function of P. That is a field along equatorial line. This is a field along the axial line. So we have resolved this, that is component into two components. So here you have resolved this. If it is resolved into two components, these two also gets resolved into two components of what is that perpendicular direction like this. So when you replace by P, that is if you write P as P cos theta for a horizontal line, for horizontal component. If you replace P by P cos theta as a horizontal component, this becomes an horizontal component for E1. That is E1. If you replace P by P cos theta, it becomes horizontal component for the potential, that is for this field. Similarly, if you replace this by, that is called as what is that? Sin theta for the vertical component. So if you replace this by this, what is that? There is P sin theta. So this is what is that field. This field is called as vertical component. So if you resolve this P into two different components, the field also gets resolved into two different components, vertical component and horizontal component. This is horizontal component of the field. This is the vertical component of the field. Now represent these two fields at this point of reference. That is a point of study. So now recall this again, the directions of this field. What you have derived. So the direction of this, I told you, that is a P direction and D directions are the same. That is the direction of the field as well as the P. That is a dipole moment. Same direction. Therefore, what is the direction of the field and the that is potential, that is dipole moment, same direction. This is the direction. Therefore, this is the direction of the field, same as the direction of this. So this is direction of the field. That is why we are indicating this direction at this point. Look at this direction of these two fields are in the opposite direction. Take all the derivation in the equatorial line. We have shown this is the direction of the field, this is the direction of the dipole moment in the previous class. They are not in the same direction. The dipole moment and this field are in the opposite direction. So, if you write what is that, this is the field. Now, what is the direction of the field at this point? See, what is the direction of the dipole moment? This is the direction of the what is that? This should be the direction of the dipole moment. The line like this, because it is parallel to this. Direction of the dipole moment. At this point, this must be the direction that is not shown here. Direction of the dipole moment. If this is the direction, it should be, this field should be opposite to that. That is, this component should be opposite. This is the direction of the field at this point. That is why, just to understand what should be the direction of the field, this should be the direction of the field, E2. So, with this knowledge, we have shown a direction of the field, direction of the field. These two are vertical. So, at this point, that is other way. We have seen that the field in the form of two components. This knowledge has come from this knowledge. When you resolve this into two components, this must have been resolved into two components like this, perpendicular to each other. There is a field components. And magnitude of the field already we know that. That is a horizontal field, is a vertical field. Horizontal field is this one. Vertical field is this one. So, find out what is the resultant of the field. At this point, I want result. There are two components. I want what is the resultant of the field like this. So, how do you get the resultant of the field? You get by vector sum. By summing the vector sum of these two. So, this is the direction of the vector, direction of vector, this is a resultant vector. We have found that this is a vector. What is that? We have found this is a vector. We need to find out what is the magnitude of this vector and the direction is this direction. We have identified at this point. So, this is what you have calculated about this vector. What is the magnitude and the direction? Direction is theta plus alpha. I'll tell you what is theta plus alpha. I want to calculate what is the magnitude of ER. Magnitude of ER, that is by summing these two vectors. Vector sum of this. So we add this vector using this formula. So this formula has come from what is that? Vector addition of, that is parallelogram, standard form. For the vector of, that is for the direction of two vectors in this fashion. This is the formula. That is from the addition, that is parallelogram addition of two vectors, standard forms. So that is E1 is this, E2 is this. Add this using this equation. You get a resultant vector. That is the vector what you need. What is that? Electric field. When you add this using this, you get the magnitude of the field at this point. So go for what is simplification. Substitute for this. Substitute for this and simplify what we get finally and see that. For simply what is that? Substitution for this E1 is what is E1? This is E1. What is E2? This is E2. Substitute them. What is eta? That is theta, angle between these two. Angle between these two is right angle, that is 90 degree. That is cos 90 is 0. So this becomes 0 and this reduced to this equation. Simplify this. So I simplify simplify by taking common factors because the terms in the two terms they have, there are common terms are there. Take them as common factor and take it out of the root. The common factors are Kp by R2. That is Kp by R2 is taken out. So remaining the root is 2 and cos square, and in the second term sin square. That is 2 whole square is 4 cos square theta plus sin square theta. Now we can write sin square theta in terms of cos square theta. The sin square theta is 1 minus cos square theta. So when you simplify or just adding this, this becomes 1 plus 3 cos square theta. So the overall equation now it becomes ER. What is ER? Resultant vector, or there is a resultant electric field, and it is the amount of field at this point. At this point, due to this dipole, it is in this case. That is the expression. So it is in terms of theta. So as theta varies, this also varies. I told you. So it is a function of theta. This potential is a function of theta or a function of position of the point in the space. This is a mathematical expression for a field at the point in the space in general. What is the direction? I want to find out what is the direction of the field at this point. Direction of the field is this direction. The direction is represented in terms of the angle. So with respect to this P, that is theta plus alpha. So this is theta. This again, what is that line is making angle theta with this. Total angle is theta plus alpha. Let us write alpha in terms of theta. Calculate first alpha. What is alpha? Here alpha is here. This alpha is making angle with this line. That is resultant component with the horizontal component like this. So this is a line. To calculate this, again you make a geometry with this. Draw a line perpendicular to this like this. Similar to this, parallel to this. A line perpendicular to this. Similar to this, what is that? Like this. So this line is same as this line, parallel. So this must be also E2. If you draw a line like this, this also E2. And then now will become what is that? A right angle triangle with this angle. This is opposite. When you draw a line, this becomes opposite side, this becomes adjacent side. Taking alpha as tan alpha, taking alpha as tan alpha, there is tan alpha. So it is opposite by adjacent. Opposite by adjacent. Opposite is the same as this. Knowing E2 and E1, substitute for them. So E2 is this expression, already you know that expression for E2, expression for E1, substitute and simplify, get cancelled, sin theta by cos theta, 2 remains. That is tan alpha is equal to tan theta by 2. So what is alpha? Alpha is equal to tan inverse of tan theta by 2. That is alpha in terms of theta. So direction, what is the direction is theta plus alpha with P. Theta plus alpha in the line of P. That is the line of P is this. This is the line of resultant. The angle represented direction of the vector. The direction of the vector is theta plus alpha. It is theta plus tan inverse of tan theta by 2. This indicates direction of the field. This indicates magnitude of the field. This is how we have arrived at the derivation for the field at that point. Now let us go for what is the derivation for the field at this point. It is potential at this point. Derivation for the potential at this point. Let us apply the same technique what we applied. At this point, there is also what is that resolve the potential into, like what is one field, resolve the potential of the field into two components, two vertical components like this. So the symbol for the potential is V. V net at the point is what is sum of this? Sum of these vector additions, sum of these quantities, the horizontal component and vertical component. Horizontal component, that is potential due to horizontal component, potential due to vertical component. Now recall the previous class. The previous class is what is the potential for the horizontal component, potential for the axial component. V1 is equal to K P by R square. Potential for the horizontal component in the previous class you have done. This is the expression. That is a dipole moment, that is a potential. If you replace P by P cos theta, that is P cos theta for the horizontal component. So this becomes what is the potential for horizontal component. This is potential for the axial line. If you replace P by P cos theta, that is the horizontal component. This also becomes horizontal component, a component of horizontal. That is V1 is a horizontal, V1 is this. Similarly, find out what is V2. Recall the derivation of potential along the equatorial line or vertical line. This is derived as zero. So potential along the equatorial line is 0. So therefore the potential along the potential of the vertical component must also be a 0. That is V2 must be a 0. So net potential at the point is V1 plus 0. So V1 is this. This is the final expression what we get here. This is the final expression, that is a potential. V is a net potential. So mathematical expression for the potential at the point in the space. At the point in the space, it is due to this dipole. So this is a potential expression. This is only magnitude of this. It has no direction because it is scalar. Potential is always a scalar. So this is how we arrived at the expression for potential at any point. That is what we are looking for. This is one. So now let us move on to the other term. That other term in this subject is torque. Let us understand. Let us understand the meaning of torque due to dipole. The torque, meaning of torque due to the term torque due to dipole. So when you take a dipole in a space, as you know, when you take a dipole in a space like this, dipole in a space, the dipole will create its own electric field around the space. And we have derived the expression for the electric field at all points, that is along the lines, all over the points, that is electric field. Now we need to talk about, if you place that dipole in the space where the electric field is already present, that is called as external electric field. So diagrammatically your depiction is there. What is that? You are representing the diagrammatic representation of this. These lines, parallel lines, says that electric field is also called as an external electric field. These electric fields are generated by what is that? Some other material. Already field is there in the space. And the direction is what is that? The line that is a arrow is the direction of the field. And this field is uniform field. What is meant by uniform electric field? Uniform electric field, what is meant? In that space, that is, in that space what the electric field is present now. If you find intensity or what is the strength of the electric field at any point It is same all over. So at every point the intensity remains same. It is known as uniform electric field, an ideal field. So, and the strength is, what is that? Uniform strength, you write the parallel lines at equal distance. And the parallel lines, if they are, what is the thick, represent what is the thick or what is the distance of separation, says the intensity of the field. So this is electric field. In this electric field, we have kept what is that? The electric dipole. If electric dipole is kept, it has its own electric, what is that field? Already field is there. What will happen? So this dipole has two charges, plus charges and minus charges. As you know, the plus charges moves in this direction of the electric field. Plus minus charges moves in this direction, in the direction opposite to the field. Recall that's Coulombic force. So this is a Coulombic force operates in this direction. This is a Coulombic force operates in this direction, in the opposite direction. Coulombic force. So these forces are in the opposite direction, but they are of equal forces, and they are not acting at the same point. They are acting at two different points, and these 2 points are joined by a line like this, fixed by this line. So what will happen by the effect of these 2 forces in that electric field? What will happen? So because of this, what is that? This point is pulling in this direction, this point is pulling in this direction, resulting, what is that? A net force. So this will result, what is that? This dipole will remain over there, but rotate about its own axis. That is the effect is produced. So because of these 2 forces which are acting in the opposite direction at different places, there is no other option. So it cannot displace. The dipole will remain over there, but only can rotate in that plane or space about this axis. So the rotation is called as torque. The torque of the dipole. So dipole is keep rotating due to this interaction of the electric field, due to this, and electric external field like this. So this is known as torque. The symbol is T. The magnitude of the torque we are estimated as is a product of F and D. Let us find what is F and D. What is F and D? So let us find out what is F and D. F and D, it is a force acting in this direction, this direction. This is the same force. The Coulombic force. Recall the different, what is that? A relation between the field and force. Field is equal to force by Q, or force is equal to EQ. So force is equal to EQ. What is this F1? E into Q plus, because of this plus. F2 is equal to minus EQ. Minus is because of minus Q. So minus and plus represent 2 different, there is opposite direction, but the magnitude remains same, EQ, EQ. So magnitude of F is equal to F1 is equal to F2 is equal to F is equal to EQ. That is a force, either this force or this force. That is F. That is F is this. And let us write what is D. So in this torque, D is this line, that is a perpendicular distance between these 2 forces. So these 2 forces are, this is the line, the perpendicular distance, that is the perpendicular line is this is called as perpendicular distance. So this is a perpendicular distance. You have to find out this distance in terms of theta. What is theta? Theta is the angle between this line and this line. This line is called as dipole moment. Dipole moment is along this line. This line represents external electric field. So theta is the angle between the dipole moment and the external field. Angle between P and E. So for this, what is that? To evaluate this using this geometry, that is a right angle triangle. So you can evaluate what is D, that is taking sin theta, theta is sin theta. So sin theta is equal to opposite by hypotenuse. Hypotenuse is what is the distance of separation. So this is L between these two, that is 2L overall. dl by 2L. dl by 2L. That is D is equal to 2L into sin theta. Substitute for D. Substitute for D. That is F is equal to EQ. D is equal to 2L sin theta. So we get what is that EP sin theta. Because Q into 2L is P. EP sin theta. So that is a mathematical expression for a torque due to dipole in the external field. Magnitude of the torque is equal to magnitude of the, that is depends on the magnitude of the electric field and the magnitude of the dipole moment of the dipole and the angle made between the two fields, theta. Mathematical definition. Very interesting point is that, so we have three different quantities are there, that is T, P, E, all of them are vectors. So this is a vector, vector, vector into sin theta. So this is a standard form of this. In vector, it is known as cross product. It is known as cross product. Cross product means multiplying a vector by a vector, you get a quantity known as another vector, not a scalar. It is called as cross product. So formula for the cross product is, that is P into E into sin theta. That is the formula. It is same as cross product. That is, it is a very good definition. It is a very good definition for cross product in physics. That is a cross product, vector cross product. So torque is a very good example for the cross product of two vectors. So similarly we have one more product is there, one more type of product is there. It is a dot product or scalar product. What is that? That is a dot product means a vector into a vector. A vector is multiplied by a vector. We use one more quantity. That quantity is never a, what is that? Is not a vector. It is only a scalar. That multiplication is called as dot product vector or scalar product of the vector. So the example in the physics is work. That when you multiply force by displacement, not distance. Displacement is a vector, force is a vector. When you multiply, it gives what is the work. Work is not a vector, it is a scalar. So that is a very good example for a dot product of vector. That is the application of mathematics in physics. So this finds what is that? A very good example for the cross product vector is a torque. And W is equal to force into displacement is a very good example for what is that? A dot product of the vectors. So let us see, this is the direction we know, but what is the direction of the torque in this field? What is that? So we know that this is the direction of the field. What is the direction of the, what is that P? This is the direction of the field. So if we say this is in the plane, these lines are in the plane, this line also in the plane. In this plane this is rotating. So in the plane the direction is this is the direction of the dipole moment. So what is the direction, what is the resultant is a torque because of these two vectors. So these two vectors, the resultant is, what is the product is the torque. What is the direction of the torque? The direction of the torque is what is the perpendicular to the plane. Perpendicular to the plane about this point. That is the direction of the vector. So that is a torque is a vector. So this is how we represent, that is geometrical representation or the magnitude as well as direction of the torque. Magnitude is this, direction is perpendicular to the plane in which what is that the torque is rotating like this. So torque, what is the meaning of torque? Torque means actually it is what is a net force, net amount of force, the resultant force which is arising out of these two forces, which will drive this dipole to rotate. It is called as torque. Torque is what is that rotating force which is arising out of these two forces. It is known as torque. Meaning of torque. Magnitude of the torque is this. Direction of the torque is the line perpendicular to this point, perpendicular to this direction as well as this direction. And this torque is also oscillating between two values, the minimum value and the maximum value. So when theta equals 0, t becomes 0, that is the minimum value. Theta becomes means when this line is coincident, it is aligning along this, no torque. When theta equals 90, t equals p into e. 90 means sin theta is equal to 1. So it is a maximum value. So always what is that rotation in the field always in this direction. It is always clockwise direction. So rotation direction is clockwise. That is the amount of rotation, that is force exerted by the torque. And mathematical expression is this is a mathematical expression. Using this, we have set so many problems on this. We have 4 different quantities, t, p, e and theta. Knowing any 3, other can be calculated. There are set of problems on this. this. So this is the meaning of torque, very important terminology. So with this you have completed. Thank you very much.